Hey everyone, I'm Gautam Karthi, a growth engineer at SigNoz. Today I'll show you how to instrument a Llamaindex-based RAG app using OpenInference and send that trace data and log data over to SigNoz Cloud, giving you full visibility over your LLM pipeline. Let's start by seeing the app in action. This is a very simple front end connected to our RAG-powered backend by Llamaindex, trained on our SigNoz developer docs. So any questions that you ask here should be able to be pulled from our SigNoz developer docs and shown in a nice, easy-to-read way. Let's start by asking a question like, how do I instrument my Python application and export that data to SigNoz Cloud? This obviously takes some time because it's querying or retrieving against our vector store, which in this case is in memory. As you can see, we get a nice formatted response with some clear steps on how to do that. Let's say in this case, I did not like the feedback. We also track feedback on these messages, and we'll be able to see that in our logs and in our dashboards later on in this video. So far so good, but how do we know what's actually happening under the hood? That's where OpenInference and SigNoz comes in, which I'll show you right now in our code. In this case, we're using the OpenInference specific for Llamaindex, in which we're importing a Llamaindex instrumenter. Obviously, before this step, you would need to pip install this package. What we do here is split up into two steps. One is actually configuring our exporter, and then the second step is actually instrumenting it using our Llamaindex instrumenter. So we can start off by creating a resource and specifying the service name for our traces. We can provide a tracer provider with that resource, and then we can create a OTLP span exporter. Here's where we set the endpoint for our specific cloud platform, SigNoz Cloud Platform. In this case, since I'm using an Indian region for the platform, I would do a .in, and then we pass in our SigNoz ingestion key as a header also into this span exporter. Then we go ahead and add that span exporter as a batch span processor to the provider. And when we actually go ahead and instrument our app, here is what we do. We call the Llamaindex instrumenter from OpenInference. We call the instrument function on that, and we pass in our provider that we had earlier set up. This is what will tell OpenInference the location of where to send the trace data that's automatically collected from our Llamaindex application. Let's go to our SigNoz dashboard and inspect what happens when we make a query and what happens when the application is started up during that docs ingestion process. Let's first start by taking a look at our logs. As you can see, let's move this to the last 30 minutes, as well as label filter by our service name. In this case, it's Llamaindex RAG demo. And we can see a series of, let's actually make this last 1 hour, just so we can get a little bit more info on what's going on. During our docs ingestion process, we see a variety of logs that are being auto-emitted, and these are calls to OpenAI's embedding API. We also see when the docs are finished, embedded, and indexed, and when we click on the docs, we can see various important information, such as the number of chunks that are being produced, in this case, 1,240. We also see when the query is starting from the user against our docs, and if we click on that, we can see that it's taking a similarity top K of 2, meaning that it's going to index and try to produce the 2 most relevant document results. As you can see, during the query process, it makes 2 post requests, one to OpenAI's chat completions for the LLM model response, as well as another one to the embeddings for retrieving process. Then, upon the user feedback received, we get this log, and we can see whether it was up or thumbs down. In this case, thumbs down. Now let's move over to seeing the traces. We'll set this to the last 30 seconds and filter by service name equals Llamaindex RAG app OpenInference, which is the name that I'd set again in my Python application. We can see a list of things that are being called in the list view. These are all the spans that we see, but for a more easy view, we can move it to traces. Let's actually make this a little bit longer. As you can see, we can see a bunch of query calls here. These are when the users are actually inputting information into the LLM and pressing enter and waiting for the query to be answered. And we see these 2 important functions, sentence splitter and OpenAI embedding. These are the 2 calls that are actually done during the docs ingestion process. Sentence splitter is actually responsible for splitting the documents that are uploaded into chunks, and embedding is what actually converts each chunk into an embedded vector. If we go into our sentence splitter, we can see some pretty important information. We can see all the spans that the sentence splitter was split up into, in this case 460. And if we go into them, we can see in detail each call to split text metadata aware. What this essentially is doing is for each document that we have uploaded, in this case around 460 documents, one for each of the markdown file that's in our entire SigNoz developer documents, we can see that each document is being split up into chunks. For example, if we go into this one, we can see some important attributes. We can see the input value, we can see the output value, and we can see our service name, like I've said, as well as the language. In this case, it's Python. Some interesting information is when you go to the input value, you will be able to see the file path that's given. So in this case, for this specific vector or this specific chunk split, we can see it's splitting the alerts management / alerts history markdown file. So in this current function, that's the file that's being split up into chunks. And if we go to something like this, we can see we are getting the notification channel / Slack markdown file, which is another file in our SigNoz docs. Another very important thing is we can see the duration it takes for each step of this process. We can see that the total process took 937 milliseconds, close to 1 second, and we can see the time it takes for each document to be split. As you can see, most of them are under half a second, even under 1 millisecond. Now let's go on to our next step of the docs ingestion process, which is our embeddings. So if we go into there, we're able to see some more important information. This one is not split up into any total spans, but we can see some very important attributes. We see a list of all the embeddings that was generated from our chunks. So in this case, again, we see 1,239 numbered embeddings, but since it's 0 indexed, we have a total of 1,240. For each embedding, we get the actual vector value, which is an array of these crazy float numbers. But more importantly, we can see what text is in each embedding. So for this embedding, the last embedding, we see that this is the file path. We have all the information as well as the actual path that that embedding redirects to. And we can get this for all of our embeddings. Super useful information, as well as we get the SDK language again, as well as our service name that I had talked about earlier. Again, we get the duration of this entire process, which took around 14 seconds. And lastly, let's take an example of one of our queries and see the steps it takes for that. During a RAG query process, consists of 2 steps. There's a vectorizing step, as well as a synthesizing step. As you can see, the vectorizing retriever step, we can go into that and see some useful information. We can see things like the input value, which is the question that was asked. We can also see things like the output value. But more importantly, we see results or metadata for the 2 top relevant scores that were produced by the query engine. We can get the actual context, which is the text of that document. We can get that document ID. And most importantly, we can get a document score, which is a relevancy score from a scale of -1 to 1. 1 being as relevant as possible, and -1 being actually inversely relevant or common. As well as we see for document 0, we get one for document 1 as well. Hence, we have K similarity of 2. We also get the score for that document as well. And we'll be using these scores in our dashboard, in which I'll show you shortly, and it's really to evaluate the performance of our LLM RAG pipeline. If we go deeper into our synthesis step, this is where it actually creates the query. We get some pretty useful LLM-specific metrics over here. If we go all the way deep into our OpenAI.predict, we can see that there is the OpenAI.chat. And this is actually the call to the chat completions API on OpenAI. And we get some pretty important information. We get things like the total token count, which we'll keep track of, and that's split up into the token count for the prompt as well as the token count for the completion. We get the actual model, which in this case GPT 4.1 mini. We get, the role, in this case assistant. We get the message content, which is the entire message history, and we get all the input values and output values. Super helpful. SigNoz also allows you to create dashboards from these traces and logs, which I just showed you, to create custom dashboards using all these attributes so that your observability scales with the app. It really gives you more insight to visualize this data. So now if you go over to the dashboard section, you should see this dashboard, which is something I created specifically for demo purposes. And if you set this to over the last 1 week and refresh, you will be able to see some pretty important information from an LLM developer perspective that you'd want to keep track of. Number 1 is the docs ingestion duration. So it'll just keep track of the amount of seconds it took for the entire documents to be ingested during our RAG pipeline at the start of our application. So as you can see over the last week, it'll give you some values during those days. When there's a straight line like this at 0, it's essentially it's downtime or the service is not being used. So there's no data to really track during those times. We can see things like 69 seconds it took over here in this specific ingestion period, but the average would be around this less than 50 range. One thing you see here is a spike to a whopping 100 on August 1st, 11:15. And so from a developer perspective, you would see this as a red flag, and you'd want to go into the traces and logs or your overall event tracking for that specific time period and see what really went on to create that type of outlier. We also have a similar table like that for except the query duration. So every time a user makes a query, how long is it really taking to get a response? We can see again, there's a pretty tight range. Most of them are sub 20 seconds, but we can see some outliers. Again, in this case, it was 33.6 seconds. So there could be various reasons for this, such as a lot of requests being made at the same time or network errors. So this could be something that you would want to investigate. We also get some distribution metrics. We get a pie chart for the type of models that are being used for the LLM portion of the query process. We can see here that majority was GPT 4.1 mini, but we are using some queries were made using GPT 4.1 nano and GPT 3.5 turbo. We also get the specific distribution for the embedding model that we're using from OpenAI, which is the model used to actually embed the vectors from our documents. So here we see that majority was actually done on OpenAI's text embedding 3 small model, and a small percentage was on the text embedding 3 large model. We also get some pretty important information from the querying things as well. We get 1,240 chunks processed during the document ingestion, and we keep track of the average similarity score of our first ranked document as well as of our second ranked document. And this is pretty important because the higher that these values are, you know that your LLM is providing accurate information to the user's queries. And the lower they are, you might need to think about either uploading more documents during this ingestion period or maybe tweaking your LLM in a way that can provide more relevant information. We also keep track of our top K document retrieval, hence we have first and second ranks for K equals 2. Here is a distribution score of our user feedback. So we keep track of the amount of thumbs up and thumbs downs that our users give. Overall, just to keep track of how user-friendly our LLM really is. And the more green, obviously, would be the more better performing our users think that our answers are from our RAG chatbot. Then we have a queries in period table. So this is basically keeping track of the query frequency, in this case, over the last 1 week. And we see again that these lines are during downtime, so there's no requests being made. And these spikes are how many requests are being made in that specific time period. We can see, for example, over here, around 1324, there were 8 requests made on July 29th, around that time period. And so this could be used really efficiently to track activity of your chatbot and really how many users are using your chatbot and how many queries are being made. And lastly, we have our total input and output tokens being used by our LLM. This is super useful in just determining the usage rate of your application, as well as it can be used to look into things like payments and how much your APIs are being. So just to wrap it up, we added production grade tracing to our RAG app using Open Inference in just a few lines of code and visualized everything in our SigNoz cloud platform, from logs to traces to even these dashboards. It's easy, powerful, and gives you end-to-end visibility into how your LLMs behave. Thanks for watching, and try it out and start tracing your AI applications today. Thanks, and have a good day.